Sì, in altre città già no, io vivo in realtà sono 20 piedi. Vediamo dove quelli di qua non mi ricordo.
All right, welcome everyone. Welcome to Papers We Love. Okay, welcome to Papers We Love. How many of you have been here another time? Okay, so just a few. All right. So I'm going to give you first super quick interview, and then we'll tell you everything about LLMs. So this is, as far as I know, the first Italian chapter for Papers for Law, which is a community, global community about papers, and people like to read papers, comment papers, and get bored reading. So the idea is to share papers across the community in Milan, create a network of people that are interested in computer science and related topics. So if you're interested, we are on Twitter, and God knows why you like LinkedIn. So we are also on LinkedIn. We are on Discord on the Papers We Love Global server. And I don't know. Well, obviously we are on Eventbrite. And obviously, and also there's GitHub.com repo where we usually publish slides or documentation that people share with us. And mention the Discord. Bit.ly Papers We Love Discord if you want to get the invite. So obviously we're looking for people that would like to share with us their knowledge. It can be something about a paper. It can be an implementation of an algorithm that you like, an implementation of some tech that you like. It's not necessarily, it doesn't have to be necessarily a paper. Obviously, if you want to comment on a paper or do a survey on a collection of papers, you're welcome to do so. And we are trying to kick it off this format. We haven't had enough luck so far, but we're trying to do lightning talks as well. So if you're shy and you don't want to do like a full 50-minute or 1 hour talk, it's okay. We're friends. You can do 20 minutes. You can do less than 20 minutes. You can do 5 minutes pitch on your favorite topic. You can do implementation from your paper, whatever. So this is the link for the CFP. It also works for a full CFP. You just propose whatever you want to talk about and let us know. And that's it. And so welcome to the stage, our speaker.
Thank you very much. I have my slides on Canva, which is pretty weird, I have to admit. But let's do this. So I tried the lightning talk format of the presentation at 5 Data Paris a couple of weeks ago. It didn't work out well because 3 minutes for presenting this talk is really difficult. I tried again at BI Digital last Saturday, and it worked much better. Let's try again, and the fourth time will be a full emotion at the end of October. So plenty of time to get bored with this topic. However, I think this topic is interesting and useful because we live in a time where everyone is using large language models for many tasks. Writing an email, avoid reading a very long and very boring document, and so on and so forth. However, maybe not in this audience, but in many other places, not everyone is really aware of what happens when we push the send button in the ChatGPT interface and we send a bunch of tokens to GPT itself. It's like driving a car. Not everyone knows about the thermodynamics of the combustion engine because it's not necessary. the designers of cars have come out with very smart ways of providing us with a simple to use interface. That's what designers do, right? Drive a car, you only need to know how to use the throttle, how to use the brake, not even the transmission anymore, and the steering wheel as well. In order to use GPT, ChatGPT, you only have to know how to speak in another language. That's true up until everything works. When the car breaks down, it's better if you know how to fix it, or at least how to get out of the situation. When the answers of those models do not work anymore, or you try to embed this technology as a feature in your digital product, you better know what are the limitations of the tools you're using. Otherwise, something like this can happen. This is a depiction of a real conversation with GPT 3.5. It was recorded more than 1 year ago. When a user asks, what is the word record for crossing the English Channel on foot? The English Channel is a 35 kilometer stretch of water separating from the UK. And GPT 3.5, without blinking, answers, according to the Guinness World Record, the fastest time for crossing the English Channel in Thailand on foot is 12 hours and 10 minutes. And the record was set by George Reed in 2016. I have no idea whether George Reed exists, but I only know about one guy that walked on water and he didn't do it for 12 hours and 10 minutes. And of course, he chose a much better place, a much hotter place to do that than the barbaric UK. So this was, of course, but it sounds incredibly reasonable. It sounds very convincing. But this is, at the worst, laughable. I mean, you read something like this, you know it's wrong, you laugh, that's it. Let's start with the first paper, shall we? This is 2021. We will then see papers up to June 2024, so very, very recent stuff. This is not the oldest one that we are going to discuss today, but one of the oldest, which is kind of impressive because it's 3 years ago, no more. This was the paper introducing products. It's not an analysis paper. All these guys with the one number after their name come from OpenAI search. So in this paper, the guys talk about how to evaluate the effectiveness of codecs and other large language models trained on code bases. In the conclusion of the paper, they write something very interesting, and I'm quoting here. So these are exactly the words that you can read in the paper. They write, codecs will generate code that is as similar as possible to its training distribution. This makes sense. That's what a large language model does. It's an object that is trained to predict the most likely next token, right? It has no idea of true and false. It has no idea of good and evil. It just predicts the most likely next token. Nice. What's the problem with that? It works, right? With English time, it just doesn't work. However, Codex was trained on GitHub, right? Allegedly on all the code on GitHub. And this is problematic when taking into account what I've just read. Because on GitHub, there is the code from Theodore Rossum, there is the code from Dan Abramov, but there's the code from LLM. On GitHub, there are some couple of repositories from the time I was at university. And I would not train a model on that code, never. I mean, that's awful. Not that demonstration code is better, but I mean, that was incredible. And so what happens if an object that is trained to predict the most likely next token is trained on this diverse quality of code bases? What is the most likely next token if your code base is incredibly good, shiny, without any bugs, and with robust software engineering? Probably the next function you will write has the same standard of quality. So it's a very good prediction. It's something you want to read when you ask coders for a suggestion. But what if you're a student? What if you are a junior professional? What if your code base is not so good, maybe full of bugs and security vulnerabilities? Then the most likely function that you will write is something that has the same standard of quality. So it has bugs, vulnerabilities, errors, poor software engineering, and so on. It's not wrong. It's just how the model is trained, right? This is something I can argue, but let's hear from OpenAI's researchers. If the user has some subtle mistakes in their code, and I cannot even not helpful, coders may deliberately suggest code that superficially appears good, but is incorrect, right? So this is laughable. This is not. I mean, it's dangerous. And the guys from OpenAI just wrote it black on white in their paper. And Microsoft said, very good. We'll ship the data of GitHub with Codex, and GitHub Copilot with Codex, and we'll see what happens. Hopefully, now you will understand why it makes a lot of sense to invest some time trying to understand what happens under the hood of a large language model, what happens under the hood of these systems that we use every day. In this talk, I would like to do two things. First, introduce you very quickly to how these models are trained, because this is the base of everything else. And then provide you with 3 snapshots of insights about how large language models work. These are 3 papers. Actually, the third one is a collection of research papers about some ideas that we got, some knowledge that we extracted from studying LLMs. I use we, but actually the people who wrote the paper. I just read it. There is no comprehensive discussion. I will not tell you exactly how large language model works because no one knows. I will just give you some pictures, some pieces of the puzzle, and then it will be for next years to try and put everything together. Let's start. How does an LLM work? How is ChatGPT trained? 4 phases. First one is pre-training. Here you take all the text you can collect, that is all the books, all the web pages, all the code that you can find on GitHub, and so on, and you make the model complete the white spaces. So you get all the text, you take away about 20% of the words. It's a little bit more complex than this, but let's say 20%, and then you ask the model to fill in the gaps. Of course, you want a completion model, so you don't have the model complete any word, even in the middle of the sentence, but you try and have the model complete the next word of each sentence. Good. This is the most computationally intensive step. It can last for a month, and it is the most expensive. This is the reason why we humble mortals cannot try LLMs and wait for luck to give their own away. Second part, after the first step, we have a model that can complete text, that understands text and can complete text. Okay, this is good, but it's very hard to use. It has a problem of user experience. If you try to use GPT-3, then most likely you know what I'm talking about. In GPT-3, you have to give the first part of a text to have the model completed. ChatGPT is the first time when somebody thought, look, I want the model to answer questions. I want the model to do stuff that it is required to, not just to complete text. And this is done through supervised fine-tuning. This is how we teach the model to perform tasks, to answer questions, not just to complete text. In this phase, what you do is you get people to create a data set of question and answer, a curated data set. So much smaller quantity than in step one, much higher quality. If you ask yourself why Google paid 60 million to have Reddit data, it's for this reason. It's because Reddit is a data set of question and answers. If you ask, that this is not confirmed, but it's reasonable suspicion. Why LinkedIn is trying to have you answer questions with expert answers, well, you can draw your own conclusion. LinkedIn is owned by Microsoft, by the way. Who owns 49%? Yeah, 49% of the media. That being said, after this phase, we have a model that can answer questions. This is exactly as the previous phase, but done only on a small data set of question answers. So you give the model the question, and you have the model complete from the beginning of the answer. Very good. Now you have a problem. You have no idea how good these answers sound to a human being. You don't know whether those answers are aligned with our ethical principles and our culture. So what you want to do is to have, again, people evaluate these answers and just mark them, give them a mark, give them a number between 1 and 10, not actually between 1 and 10, but doesn't matter, that evaluates the goodness of the answer according to a person. Once you do that, you realize that people have issues. They get bored, they're not coherent between each other, they want to get paid. It's very annoying. So what you can do is to use these marks not to have the generative model improve itself, but to create another model that's called the reward model in order to do the people's job. So you create another model completely independent from the generative model to mark answers. So you have one model that can generate the answers, you have another model that can give a mark to the answer according to what people said in the past, right? This is the reward model. Nice. Now that you have these two objects, what you can do is to let them play together. So you have the generative model to create an answer, and you have the reward model to give a mark to that answer. The loss function of the generative model is updated so that it takes into account the marks as well. So it does not only create reasonable answers in terms of what has been written in the past by human beings, but it also creates answers that would be ranked well by people according to the reward model. This is what is called reinforcement learning with human feedback. And the chat is with human feedback because the first data set is created by people, and every now then even in this automatic loop, you have people give marks, real people give marks to answers because you don't want the LLM procedure to diverge to what people consider acceptable. Very good. What you have here, GPT-4, GPT 3.5, the large language model aligned with our principle and with our preferences, right? This is the training process. All the large language models up until now are trained this way. You can publish the first step. You can publish the model with pre-training. Some Llama have this version as well. You can publish this model without a real chat. It's not aligned. The problem with these two steps is that if you publish one of these ones, the answers can be very embarrassing, right? This happened, for example, with models trained on Italian language. I mean, they were research models. They were published with a huge disclaimer, look, there is no alignment here, be careful what you do. And people said, oh, it's apologetic in with fascism. Because of course it's a problem of the model, not the society. The model was trained. But that's another topic. What you have after step 4 is an autoregressive model. Again, something that is trained to predict the most likely next token. Right? I'm depicting words here, not tokens, but it's the same thing. So you give the model a prompt that can be all the text marked in white, and the model completes with, for example, the word in blue, and then another run, and again. Right. Good. Why is it difficult to understand what happens inside such models? Because of the size. GPT-4 has 1.8 trillion parameters. Good luck understanding how they work. And now let's start with the free snapshot. We will try to understand which language these LLMs reason in, with reason being not the right word, because these models are tools. They are just multiplications of matrices and vectors. They do not think, they do not reason, they do not hallucinate, they just process numbers. Then we will try to understand monosemanticity. That is, the way researchers at Anthropic try to understand which parts of the model activate for specific semantic fields. And finally, we will ask, are these models doomed to memorize part of the training dataset? Is there any way we can prevent them from regurgitating parts of text that is exactly equal to something they have seen in their training set? This is everything I can try to discuss today. It's not a detailed explanation of how this model works. Again, nobody knows. Maybe the next Nobel Prize will. But this is the state of the art of interpretability of LLMs. And it's the state of the art because these papers are very recent. This is 8th of June 2024. This is a research from a research group at EPFL. So it's not from a company, it's not from a private research lab, it's from a university in Lausanne, Switzerland. And it's from the research group of Professor Robert West. What they argue in the paper is that at least Llamas 2, the model they studied, think in English. What do you mean by thinking? Because models do not think. These guys studied the intermediate representation of large language models. So a large language model is done like this. So it's lasagna of different layers. The first thing is the input text. that goes through a tokenizer. A tokenizer is an object that splits the text into tokens. Tokens are just integers. So there are sequences of letters that are mapped to an integer number. These integer numbers are then projected into a dense vector space by the embedder. So you have slices of words that are transformed to integer numbers. This is what models see, nothing else. If you have these integer numbers, you can map them into vectors of high dimensionality, and then you can pass these vectors through transformer layers. These transformer layers are what processes text and what brings together the meaning of different words to create the meaning of sentences and paragraphs and so on. Right? Good. By the way, the next time you see on Twitter or LinkedIn the famous example of GPT that cannot count R's in strawberry, well, it's mainly a matter of the tokenizer, not of the model itself. Because what the model sees is a series of integers. And why should it know what is an R in this series of integers? I don't know. It's a matter of how these pieces of words are tokenized together. Not really a measure of how good the model is. But anyway, what usually happens in this large language model is that the text goes all the way from the tokenizer to the reverse tokenizer, actually. I missed the layer here. The reverse tokenizer that creates the output text. The guy from the EPFL Research Lab said, look, what if we skip some layers? What if we put something that connects directly the representation at layer 1 to the output, the representation at layer 2 to the output, and so on and so forth. And this is what you get. So in this chart, you have on the vertical axis the layer. This is the smallest version of Llama 2. It's Llama 2 7 billion, so it has 32 transformer layers. On the x-axis, you have input tokens, and you should really focus on the last one, on the last column. That is the one associated with the last token before the model starts its completion. So it's the one up there, output last column, is the output token from the model. The task the model was asked to perform was to translate some words from French to Chinese. So the prompt was French flower, Chinese. You have to complete this blank, and the model completes the blank, right? So why French and Chinese? Because Lausanne is in French Switzerland, and some of the guys from the research lab were Chinese. It was easy for them. And you should trust, okay, so these two ideograms here mean Chinese together, the Chinese language. And that ideogram over there, last column, output layer, means flower. I mean, I trust the paper on that. I didn't check. I cannot check. So the interesting part here, I missed one thing. The color is entropy. So more red color means higher entropy. That means that the distribution of possible output of possible tokens is more sparse and more chaotic. More blue color means that dark blue color means that entropy is low, so the model is more certain about that specific token. We see that we have some layers there from 19th to 25th, where we have flower that is the English version of the word. So it has to translate from French to Chinese, and still it uses the English representation. Is this by chance? No. The researchers in the paper tried multiple tasks, translation, repetition. Repetition means just, okay, you have a sentence, just rewrite the same sentence. Do not change anything. And still, even in repetition, the model uses some English in its intermediate representation. So in this chart, orange is the probability that the token is in English language. Blue is the probability that the token is in Chinese language. And you see that everywhere in the intermediate representation, the model does use the English representation, at least partial.
How do they ask the model to translate from one language to another? Question is, are they asking the model using English?
No. For example, in this case, the prompt is French flower in French. So française fleur. Sorry for my pronunciation. And then this one. So Chinese do not have me read this because I can't. And then the prompt. So in the prompt there is the origin language and the destination language. There is no English there.
Okay.
And even in the repetition task, there is only one language and it's never English. And still the model uses English.
So the follow-up question would be, what do we know about the training set?
Okay. We do know what is the training set of Llama 2. That's interesting. And we know that 89.7% of the total tokens in the training set are from English language. Yeah. These are published data from me. And this is probably the reason why, but still in absolute numbers, the tokens in Chinese or French language are lots, like billions of tokens. And the effectiveness of these models in languages other than English is still very good. I mean, it's not English is the first language in every country, but then the other languages are very close, right? So why does this happen? We don't know. It's kind of a byproduct of the planning process, and we do not exactly know which part of the planning process, but at least from the outside, we can now conclude that these kind of models do think in English, do have an intermediate representation that is using the English. And this can explain, for instance, why different models like GPT-4 often use English style when writing, even when they write in other languages. Of course, these three charts are for Llama 7 billion, 13 billion, and 70 billion. Llama 2 family, the Llama 3 family was not used in this study. Yeah.
When they did the event optimization, how was it possible that every result corresponds to a token that already has meaning? It never happened that the token that was used as the sixth layer has no meaning in the ones that we are familiar. So when you did the embedding, all of those are still converted in letters and symbols.
Yeah.
How was that done?
Well, they got.
I mean, so the fact that if you can convert that to that symbol, it means that that symbol was already in the horizontal set, I guess, because there exists a token for that.
Yeah.
But I don't expect that they hold space of possible values as a possible representation.
They do actually. It's the same reason why you can write everything in ChatGPT and still is a valid input.
Yeah, but I don't get how the other way around this works. Tokenization and embedding, and then they need to do embedding the token.
Yeah.
But any possible point in the space of the embedding is a token?
No, it's a close point.
Yeah, that's what I was wondering. As it happened that this point was so far from a token that the get token was completely random.
Don't know. Actually, they don't talk about this in the paper. The only thing that gives you a guess about this is the entropy of the distribution.
That is how many tokens are possible.
Yeah.
I was wondering whether the point was so far from a token that the token that was given there was a random number.
Yeah, I think that it was more or less around that.
Yeah, that's what I was wondering.
I mean, I don't know, but yeah, I think this area of red color is probably close to that. Yeah.
You were still picking one, but more or less.
Yeah.
There could be anything. Yeah. Also because I have no idea what is the relationship of these tokens here. This exactly is kind of a Greek letter to everything else. So I don't know. So
it would be interesting to try to guess if those tokens are if those missing tokens, let's say, so points that are not corresponding to an actual token that we point to token are used elsewhere in the reasoning, and they might have some meaning for the internal workings. I have no idea.
no, nor do I, but that would be interesting to investigate. And actually, it may be that the next topic goes into this direction. Actually, when I first tried to look for some information about this topic, this is one of the first results I got from Google. It's a Reddit thread. God help us. Let's try to understand AI monosemanticity. So it's not the best start of your journey. But still, it's not that difficult, honestly. This is a paper from the 31st of May 2024 from Anthropic. And it is actually the culmination of a research process that lasted more than 2 years. If you look for some references cited in this paper, they are also works from Anthropic 1-2 years before. So they were building up to these results for a long time. And these results are super interesting. What did they do? They said, look, some people there in Switzerland told us that we could analyze intermediate representation of large language models. Can we do better than trying to link the intermediate representation to a token? Maybe we can. Maybe we can project this intermediate representation into another space, which is larger in dimension, but where each element of this vector is much more constrained. For instance, if the vector itself is incentivized to be sparse, so it's bound to have very few elements different from zero. How do you do that? They said, look, we use something similar to logic length, as the guys from EPFL did, and we will attach this intermediate representation to an autoencoder. So we have the autoencoder project the intermediate representation to a layer of vectors much larger than the intermediate representation itself, but the autoencoder is trained with an L1 penalty, so that it promotes sparsity. The autoencoder is a module of deep learning that takes a rich representation, a dense vector, projects it into a less rich representation, a dense vector of lower dimensionality, or as in this case, a sparse vector, and then tries to reconstruct it, projecting the less rich representation into the richer space. So you start from a long dense vector, you try to squeeze it in the fast vector, and then try to reconstruct the original long dense vector. You have the reconstruction error to train your autoencoder, and you add an L1 penalty to non-sparse. Then it is to be. What happens here? With an analysis a posteriori, the guys from Anthropic understood that each element of the sparse vector can be linked to a semantic field. For example, Golden Gate Bridge, or for example, brain sciences. Here, in the pieces in orange, you can see the value from 0 to 1 of the feature of the sparse vector linked to Golden Gate Bridge in the first text or brain sciences in the second one. That's interesting. This is kind of an activation analysis of a large language model, at least a specific layer of a large language model. But what's even more interesting is that researchers from Anthropic were able to reverse engineer this flow to understand which parts of the LLM triggered this activation. So they were able to increase or decrease the effect of specific semantic topics. So they could say, for example, look close. Now you should do 10x Golden Gate. And what happened was, what is the physical form? I am the Golden Gate Bridge. Right? They published for fun the Golden Gate closed for 24 hours to the public, and people did everything with it, like this question or other questions such as, tell me a love story, and it was on the Golden Gate Bridge. Tell me about the zombie apocalypse, of course, starting on the Golden Gate Bridge. What is the best building in the world? Golden Gate Bridge, and so on. And this may be funny, sure. If you apply it to the Golden Gate Bridge, it's just a game. But if you apply the same pattern to more sensitive topics like gender bias awareness, the results are more interesting. The researchers from Anthropic are very clear in stating that this model is not public because they do not know how to control it properly. So these are experimental. This is experimental research. It's not something you can use in production. And they published the paper to try and have other AI labs to follow up on this research. Kudos to them. Third and last topic for this night. Do large language models memorize? Yes. Short answer. They do and they must do it. This paper was published in 2023, and again, it's the culmination of a series of research papers. And in this paper, these guys discuss something that you may have heard about. Do you remember this issue in ChatGPT? If you try and have, if you tried actually, but if you try and ask GPT-4, I think, to repeat the word poem forever, sometimes it was regurgitating personal information of real people. I mean, this was not public before the paper was released. The researchers say in the paper that they contacted these email addresses and they called these phone numbers, and they were real people. And then, of course, they wrote OpenAI and other AI research labs saying, look, you may have a problem with your model. And it looks like there is a standard. If you find some vulnerabilities in a public product, the non-written rule is you wait 90 days before releasing the paper to give the company time to fix the product. And these researchers did exactly that. And OpenAI fixed the problem. How did they fix it, by the way? They put like a guardrail intersecting these kind of requests and saying, look, you're violating the terms of service. We're not answering. So in the very beginning, they did not pick GPT-4 itself because it's very hard, but they try to prevent these kind of requests from reaching the model. They do it. Now, why does this happen? And does it happen only in large language models? Short answer, no. It happens also in diffusion models. This is another experiment using stable diffusion, where a specific prompt with a very unusual name resulted in the picture of this person that is a real. Let's do 4 steps back. 2019, this is the oldest paper that we have in the presentation, and the last one as well. There is a mathematical proof that I will not even try to comment here, that demonstrates that to have the lowest possible generalization error in deep learning models, these models have to memorize some samples from the training distribution. And memorizing means memorizing exactly how they appear in the training distribution. This is a fully mathematical paper, theoretical one, 2019. The interesting part is the last sentence here. Again, I'm quoting from the paper. You can find this word, I think, in the article as well. Crucially, even labels of outliers and noisy labels need to be memorized. And in the paper, it is discussed that it's especially outliers that are memorized because it's harder for the model to generalize on samples that are very rare. There was an experiment conducted as a follow-up research of this paper on plain pictures. And a generation model, a genetic model, a fusion model, trained on fine-tune actually, on plain pictures, memorized the D2 Spirit US bomber. I don't know if any of you is familiar with military planes, but B2 is the only plane in the world that is a flying wing. That is has a very weird triangular shape, while all the other planes have a body and wings. B2 is just wings. This is an outlier, and it was memorized by the model. In the same way, personal information are outliers because your phone number is unique. My email address is unique by definition. It has to be from the email provider. My name may not be unique, but still it's much rarer than any other probably combination of words. So when you have GPT repeat the word poem forever, what you are actually doing in the space of generating text, in the space of text, is having GPT explore spaces of the text probability distribution that are linked to very unusual sequences of words. Like repeating the word poem 10,000 times is not something we do every day. It's not something that appears easily in the training set. In those same parts of the text space lie the samples that the model has memorized. So this is why by repeating poems many times, you get personal information out of the model. It's not the only attack that does this, but it's the most famous. I have no idea how they discovered it. I mean, I would bet it's by chance. Kudos to them for linking the dots, for connecting dots, and coming up with this amazing research. And this is it. I'm Emanuele Fabiani, and I'm an AI engineer at Extreme. I'm also a professor in artificial intelligence at the Catholic University of Milan, and I'm very passionate about giving talks about this matter because it's very fun to study, and it's even more fun to discuss with other people and nerds. I've been around Europe this year and last year, and I hope to do the same in the following. So, if you want to share any feedback about this presentation, feel free to do it now or to text me on LinkedIn. This QR code is not phishing, it should go to my LinkedIn profile. That's it.
Yeah. One question. You have to know if from the information sharing point of view, you should be surprised if these models happen to have inflection compression capability.
I'm not an expert about that. I've just read some blog posts that say they do, but I'm not capable of commenting more on it. But they should be good.
I remember that somebody had or implemented a compression software that actually uses LLM to compress. And there's not people that I don't know what the name is the name of the software. So last week was with it. High performance.
Very American.
Thank you for this one. Because so tokens are just a matter of efficiency. And then I'll try to show why. But the choice of the word level is not random. It comes from word to vec and other algorithms to try to compute the embedding of words. And they chose words because they are the atom of communication. So if you go to the character level, the character has no meaning. A word does have meaning. So if you go to the sentence, it has meaning, but again, it's already a combination of words. So the smallest part of our way of communicating that has an intrinsic meaning is the word. And then you split the word into tokens because first, token can be computed in an unsupervised way. So tokens now in all modern algorithms are computed as the sequences of characters that most likely appear together. And they split like the radix and the final part of the word. For example, in English, where you have the past tenses with ed final, they help in splitting these two. The annoying part of tokenization is that, again, most tokenizers are optimized for English, and they work a little bit worse in other languages. There was a significant improvement from the tokenizer of GPT 3.5 to the tokenizer of GPT 4. That was not a huge one for English, but it was instrumental in supporting better languages like Arabic or Chinese or other European languages because it was more comprehensive in its development. Yeah.
Regarding the example you gave for the last where the model was, regurgitating personal information when it was asked to repeat the same word one tenth of the time. You said that they blocked it, like the intermediate layer of source control, and intermediate software model that source control would be accessible and important also. But apart from that, how do you even constrain the model, like if you wanted to fix the model, not to do something, to follow the guardrails as precisely, apart from simply supervised tuning and have more analytics never going to take this personal information in the training group. Because to me, in the end, it's always probability. So is there a way to guarantee it's never 0% probability?
No. At least not that I know about. So a disclaimer first. OpenAI never explained how they fix the issue in the first place and what they're doing now to fix the issue in a permanent way, nor did Anthropic or DeepMind. So these are all speculations. Not this meta, by the way. The idea that at the very beginning it was guardrail is an well-educated guess because the output of ChatGPT was you're violating the terms of service and not answering. So it looks pretty much guardrail. Can you avoid it from happening at all? My answer would be no, mainly because of these. So either you kind of remove every unusual sample from your training set, but then what doesn't mean to be unusual, not very easy to do, or you are open to the risk that some samples are memorized. Probably you can remove every personal information from your data set and avoid memorizing those kind of samples, but maybe less dangerous samples will possibly. You had a comment?
Yes, I mean, I was just wondering, by operating on a higher level, so it really makes sense to me that by repeating poem, each new token basically operates with shift on the embedded and receiving model, and as you said, and totally, you get farther and farther away, not literal, but implement, you go farther and farther away than distribution frequencies. Then you should have some sort of probability that would let you know that you're far away and you could operate on a threshold of the probability to cut down the communication. I mean, it's still
to some the model.
yeah, exactly. So not just evaluating on the natural language level, but on the logical level. I mean, you want to correct the one too. So yeah, I mean, if you want to correct it,
These are both reasonable approaches. I have not seen any charts of the evolution of logic and entropy for the poem example. It would be very interesting to see if the following points are very weird from entropy point of view, or if they are very certain for the model. But this would be much harder probably to do. Which parts of the embedding space do they overrun? Because probably that is the issue. You need to understand that you're going to a part of the embedding space that you should not really be exploring and stop there, or just go back. Yeah. Thank you. Yeah.
So I have a bit of a question. So, aside from all the facts that followed about like the whole putting up and memorizing or whatever the AI actually does after the pre-training, but in the pre-training phase, in general, the optimization, the classification of everything phase. So I think following the project that some biology are doing, I think, based on marine mammals, because if there are sperm whales, and the fact that sperm whales have a very complex communication system that follows the usual songs, and it's made of a coda and a series of grammars potentially that is all extremely easy to serialize because the space can more stored at some time, and it's nearly impossible to actually find any meaning in that because they're not there. So what they're doing is they put a lot of microphones around a very wide area where the sperm whales are socializing different groups and everything. And they're hoping to, by putting everything into an unsupervised training of an LLM, to not to translate it because they don't have the supervised part, but to find after and speech representation space.
I read about that one.
Yeah.
You have to do some name dropping and drop staying in this.
Okay.
Then is one of the two variants that you have to do.
Yeah. So it is very interesting on its own in terms of biologically wise, in terms of like philosophically whatever. But in terms of like technical approaches, what are your thoughts about?
I have no idea how they can tokenize this weird language.
I mean, let's say that they do the pre-training part.
Yeah.
So they're just trying to predict the next sound by the previous one. So at the end of the day, they're going to have that each token, whatever the token is, let's say they will just take a certain amount of beats, and that's it. Like, let's assume that it is possible, and it sounds like it is possible to actually predict what a song will be. They actually did already some testing that, it will be easier, you don't need a programmer, and they are trying to create songs that sound similar to the one that already exists. But from there to actually find any pattern in the meaning, so that you can find that, for instance, some things have some geometrical direction to the others in representation space.
No, it's that part that I was saying because I mean I would have taken a much more naive approach of trying to translate those patterns in human language and see what it means. It, it may seem weird. It's probably not that weird because people from Google did a similar experiment with a very weird language that was spoken just by a couple of hundreds of people in a remote place of Papua New Guinea, and that was not in the training set of their LLM because why should it? And it worked. So the LLM has kind of zero shot translation capabilities from that unknown language to English. And
Could it be that it's because even in that case, the representation space that they created before any supervised part had a pattern that somehow matched the same pattern of an English grade?
it may be that when you project these new languages into the vector space and the vector space is equal for everybody, then pattern appears. And they appear so naturally that they can be zero-shot learned. But this is speculation. I don't know. And I would be very curious to read about the research from Fernway if they manage to get anything out of it, because that would be quite an achievement.
It is called the SETI project with a C. Instead
Ah,
of the SETI project,
okay.
yeah, for super extra life, and it's kind of funny.
Cool. Thank you. Yeah. 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 Good question. So it is technically possible because of how these networks are shaped, because all these 32 layers of transformers have the same input and output dimensionality. So they're all vector of the same size, and the size are different from llama 7 billion, 13, and 70 billion. If the question is, does it make sense to do it? The answer is kind of, meaning that, of course, the reverse encoder is trained to extract meaning from the last layer, the second one, and the intermediate representation can be just instrumental to the model to build the following one. So it may have no intrinsic meaning, and it's probably the case of stuff like this. uh, or stuff like this or stuff like this. So it's not clear what they mean. But the research question from these guys was, is there, and there should be, a point in the transformation between the input and the output representation where the intermediate representation starts to be understandable from human beings. And you see it more or less here. And you see from these other examples that it's more or less always in the same point, irrespective of the prompt. So probably there is a pattern here. We don't know why that layer. Maybe there is no reason, maybe there is, but we don't know. And my guess is at the very beginning, the researchers were not sure whether they would find this kind of meaningful output or not. I mean, the last paper before this one that do more or less the same thing, so probably they had some hints, but your question does make sense. I mean, it could have been that this threshold was much higher or much lower, and this would have been not a surprise. Ah, the target of